All right. Now, so we actually have said almost everything that has to be said about LCGs. We have seen three different kinds of LCGs. We saw mixed, we saw multiplicative. For multiplicative, we saw 2 raised to k and not 2 raised to k. Right? And we know what are the conditions for mixed. We know what are the conditions for 2 raised to k. We know what are the conditions for not 2 raised to k. All right. So all those things are given to us, and we just have to know. I mean, we just need to know them, right? Now the question is, if you have to implement it, you want to do it because these are large numbers, by the way. For 17 or 22 or 31, I said that every time you multiply, bring it down to below 31. But for numbers which are 2 raised to 31, these are still big numbers. And still you could get into overflow on a 32-bit machine. All right. So somebody figured out how to do this calculation where so that there is no overflow. Again, this is simple mathematics, but the formula is here, and you need to know the existence of this. So if you were to ever write it, you go back, open the book, and implement the formula. Okay, and the formula is as follows. First of all, you cannot do this in real arithmetic. So you cannot do it in basic. Basic has no integers. Everything is real. All right. So you have to find a language which has integers, which most languages do. And you cannot, and you have to make sure that none of the calculations results in anything which is more than the largest integer in your machine. Right. So there is no overflow. And so here is the thing, ax mod m. If you want to multiply x by a and want to take mod m, then it is equal to g of x plus m times h of x. Okay, where g of x is a times x mod q minus r times x div q. Now, let me explain what these notations mean. Mod is remainder, and div is quotient. Everybody understands what is div? When you divide x by q, whatever you get the division result, that is the quotient, and that is the x div q. What you get in the bottom is the remainder, and that is called x mod q. So if you have the mod part and you have the division part, then this thing applies. Similarly for h, x div q minus ax div m applies. And so what you do is, you calculate q is equal to m div a and r is equal to m mod a, and then basically you can calculate. And so I'm just going to show you an implementation. Actually, this is the whole code given here, so you can get the code. But basically, I'm going to give an example. So let's say you want to calculate this. You want to implement this random number generator, right? So this is a prime number. So this is a multiplicative generator of the kind. What kind? This is the multiplicative generator of the kind which is modulus is not 2 raised to k. Right? And 7, and this number 16807 is one of its primitive roots. Somebody wrote a program, figured out how many primitive roots are there, and this is one of those 534 million primitive roots. All right. So this is good. All right. Now, all we want to do right now is to implement this thing. But the problem is, if you implement this without thinking, then you take a number which is close to this and multiply by this number 16,000, it will overflow your machine. Right? You have a 32-bit machine. This one is less than 32-bit. This one is less than 32-bit. This one is less than 32-bit. But the product of these two is more than 32 bits. All right. So you can't do that. So what you do is you say A is equal to this, M is equal to this. So Q is equal to M div A. M divided by A. You get this number. This is, the division is not exactly, and division is not, I mean, basically full in the sense that this is what you get the quotient and this is what you get as the remainder. right? So the quotient is Q and the remainder is R. Now for a collect implementation, now here's the thing, the test for you. If you do it right in whatever language you select, you should get X 10,000 equal to this number. All right, let's see first the implementation. The first thing you do is you figure out A and M, which is given to you, then you figure out Q and R, right? Then you have these four integers that you calculate, X div Q, X mod Q, X new is this formula. If X new is greater than 0, then X is equal to X new. If X new is negative, then you add M to it. And X is equal to mod X new M. Okay, when you add M, this can, this is so mod M. And you keep doing this basically. So this one is while X new is less than 0, X new is equal to X new plus M. So keep doing this. And as long as it is more than M, you bring it down to M. Anyway, so at the end, whatever you get, you divide by M and you get the random number. Everybody understand the pseudocode? Right? So this is the method that will implement a generator without overflow. And then you will get the correct generator. Then you will get, and you can check it out because I did program and I figured out that this is the 10,000 number. And for other generators, whoever implements it, they will have to figure it out. If you wanted to use the real arithmetic, then you will use double, and then you will do actually truncation, which basically gets it integer, and you can get it like this. So I put it on Excel worksheet, and you can put it on Excel worksheet too. You put the parameter A, N, Q, and then Excel can calculate R, and you put A and M, the Excel can calculate Q and R, and then you can put 0, 1, 2, 3, 4, 5, all the way 20,000 to 10,000 to a million rows, and it will do the calculations for you. If you program that method there, you can do it in Excel, and you can see whether 10,000. Okay. All right. So here is for you to do that 10,000 times. You have to implement this generator using a seed of 1, and you have to determine 20,000. So basically 1, 10, 100, 1,000, 10,000, and 20,000. All right. By the way, percentage sign is used in Excel for div, and then you multiply that. What is it saying? It's saying that the R times X by Q is not equal to R times X by Q, because this multiplication will be done first. So basically you have to put the parentheses at the right places if you want to do whatever you want to do. Okay, the reason I want you to do Excel is because many languages will give you the answer right there. Okay, if you use a proper language, like I used to use Simula, I don't have to write any code. I just give it the generator and implement it for me. So Excel actually requires you to program the division, multiplication, addition, and second thing is we can check it out. If you use something else, I got to learn that language first, and we got to learn that language first. And so it becomes difficult to check it out. So right now we are limiting it to Excel, and then when you're in the real life, you can do whatever you want. Basically, I just want you to know the basics here. Obviously, you will probably be not implementing a random number generator in Excel. You will probably, here thing, Excel has a random number generator. And you will probably be using that generator, in the real world. But here we just want you to know that how to implement this. All right, now here's another thing too. One more thing, like I wanted to say, when you present the results, please don't give us 2,000 pages. Because 60 lines per page for 200,000, 20,000, you know how many lines there are. So what you have to do is you have to hide. Everybody knows how to hide the rows. Hide everything other than these numbers. So we can just see those numbers. You do have to program 20,000 though. I mean, like you have to just take one thing and say copy, and as far as you can go down. All right, start all over again, copy. So you can go down. Generally, rather than one by one, you could do 1,000 at a time. So now you will know how to implement a random number generator, which is a big win. But these numbers that we generated so far they are not long enough for cryptographic applications. For cryptographic applications, which means for network security, we need random number generators which are 512 bits long, not 32-bit long. So far, we were talking about 32-bit machines and how to use the numbers below 32-bit. But what if you need, actually 512 would be very small. What if you need 2048-bit number? Okay. And that's the kind of numbers we need. For cryptographic case, okay? For simulations, you don't need it. So then there is this guy, and Tausworthe, he generated this one. His thing is he does it in binary, and the nth bit is given by a function of the previous previous qubits. So you start with n minus 1, multiply it by some coefficient, and exclusive r with CQ minus 2, Bn minus 2, exclusive r, blah, blah, blah. So this is like a regression on the previous values, but instead of addition, we have exclusive r's, and everything here is binary. So C's are 0 or 1, and B's are 0 or 1. And this is exclusive r, which is mod 2 addition, by the way. So you use the last q bit, and you get the next bit, and then use those q bits, and then get the next bit, and so on and so forth. This is also called autoregressive sequence of order q, because we take the same thing and we regress it. Basically, we're not actually fitting a regression here, but we are given the regression and we are forecasting. And this generator, again, we are not proving, but we are giving you the fact, can have a maximum period of 2 raised to q minus 1. If you take the last 2 bits, the period would be how much? 3. 2 raised to q is 2 raised to 2 minus 1. If you take 3 bits, it will be 7, and so on and so forth. All right, so let's take before we go to the example, the way to express these things is to use a delay operator. And so bi minus b, when you apply a delay operator to something, it goes up by that. So for example, if you apply to bn, it becomes bn plus 1. This is just a notation. Okay. So instead of writing bn plus 1, we can write d applied to bn minus 1, bn. All right. If we apply dq times to bi minus q, basically what I'm doing here is I'm rewriting this formula here, bn equal to this, and I'm going to write everything in terms of bn minus q. So dn is, I should have used n here, dn is dq bn minus q, right? This is dq minus 1, cq minus 1, d raised to q minus 1, bn minus q, and so on and so forth. All right. If I take out this common term, which is bi minus q, which is basically take out, then we get, and bring it to one side, we get that dq minus cq raised, and so on and so forth equal to 0. This polynomial is called the characteristic polynomial. By the way, this polynomial has only binary coefficients. All right. So this is a characteristic polynomial. And instead of d, if you write an x, then it is called characteristic polynomial. So basically, the characteristic polynomial for this generator is x cube plus, 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 and so on and so forth. By the way, minus and plus are same. Why? Yeah, mod 2, whether you add, subtract, the same thing. So I have changed this minuses to pluses here without even saying anything. So basically, that is the polynomial. Now, the period of the smallest positive integer n for which x raised to n minus 1 is divisible by this characteristic polynomial. So you take this polynomial and you divide into x raised to n minus 1. Whatever is the, So whichever value of n, the smallest value of n, will be perfect multiple of this is the period. Now we'll see an example, it will be clearer to find the period. So maximum possible period for order q is 2 raised to q minus 1, and that polynomial is called primitive polynomial. So just like we had a primitive root, now we have a primitive polynomial, and we will see examples of each of those. Here's a polynomial, x raised to 7 plus x raised to 3 plus 1. So this can be written as d raised to 7 bn plus d raised to 3 bn plus bn equal to 0 mod 2. That means bn plus 7 is plus bn plus 3, bn equal to 0. Or we can write down that bn plus 7 equal to, so this is the polynomial. Basically, bn is equal to bn minus 4 plus bn minus 7. Yeah, right. Basically, we want to make sure that the whole arithmetic here, this mod 2 applies to everything here, that both sides are done mod 2. And so if I give you this polynomial, you should know that the generator is this one. So now we can start with the seed. The seed is B0 equal to B1 equal to B6 equal to 1, all ones. That is our seed. This is the number, seed number is 1, 1, 1, 1, 1, 1, 6 ones. We put those ones and get B7 is equal to B3 and B0. We get this, B8, B9, B10, B11. So we get the next 6 numbers are these. Then we can continue. Actually, we are not doing 6 bit at a time, we are doing 1 bit at a time. But I am just writing here 6 bit at a time so that you can see them clearly. So you get all this whole sequence, and you will notice that the sequence starts repeating here. This is 6 ones, 6 ones. All right, 7. We started with 7 ones, B0 through B6. Started 7 ones, and we ended up with 7 ones. And so the period can be calculated. Period is 127, which is 2 raised to 7 minus 1. And therefore, this is a primitive polynomial. So the only way to find out if something is a primitive polynomial for mortals like us is to do this. Okay, mathematicians have better ways to do it, but for us, and we are not going to do it very, very often actually, but if in this class I ask you if it is a primitive polynomial, you just do this and figure out what the period is. If the period is full, it is a primitive.